All right, today we're tackling a really cool, elegant idea from thermodynamics, the principle of corresponding states. I mean, think about it. It's this powerful concept that looked at the crazy, chaotic world of gases and somehow found one single rule to tie them all together. So let's get right into it. So picture this. It's the 19th century. You're a scientist and you're surrounded by all these different gases. You got methane, oxygen, carbon dioxide, you name it. And every single one acts differently when you change the pressure or temperature. The big question, the huge challenge was, is there any way, any single law, to predict how they all behave? Or are we stuck making a unique equation for every single one? So here's our game plan. First, we'll look at the problems scientists were facing. Then we'll get into the core principle itself. After that, we'll see how it spawned an incredible tool for engineers, but also where it fell short. Then we'll cover the clever upgrade that fixed it and wrap up with why this idea, which is like 150 years old, is still a huge deal today. Okay, let's set the scene. We're talking late 1800s. The Industrial Revolution is going full steam ahead, and engineers are dealing with real gases, often at insane pressures and temperatures. Trying to figure out what a gas was going to do was a total mess, a case-by-case nightmare. They were desperate for a universal rule. Then, in 1873, this physicist, Johannes van der Waals, comes along with a pretty wild idea. He basically said, hey, what if all these different gases aren't actually that different deep down? And that idea, that was the seed for what's known as the two-parameter model, which down the line got a major upgrade from Kenneth Pitzer. So what was this revolutionary idea? Let's dig into the core principle. It's really all about finding a common ground, a way to compare apples and oranges. Or, well, in this case, a way to compare something like argon to ammonia. And here it is. This is the heart of it. The principle says that if you take a substance's properties, like its pressure and temperature, and you scale them against its own unique critical point, then suddenly all substances start acting the same way. The critical point, by the way, is just that special temperature and pressure where the line between liquid and gas completely disappears. It turns out to be the perfect universal ruler for everything. And this is where it gets really practical. All you do is take the pressure you're at right now, P, and you divide it by that substance's special critical pressure, PC. That gives you something called the reduced pressure. You do the exact same thing for temperature. All of a sudden, you have these numbers without any units, which means you can finally compare any substance to any other on the exact same playing field. It's kind of like, instead of comparing a baby and an adult by their age, you compare them by what percentage of their life they've lived. It creates a common scale. Now, this idea of reduced properties wasn't just some neat academic trick. Nope, it led to one of the most useful tools in the entire field of chemical engineering. Here's the killer insight. The theory predicts that any two gases will have the same compressibility factor. That's basically a score for how much a real gas acts like a perfect, ideal gas, as long as their reduced pressure and reduced temperature are the same. It's that simple. This idea gave birth to the generalized compressibility chart, and let me tell you, this was a game changer. Before this, if you were an engineer designing, say, a refrigeration unit, you needed giant books of experimental data for your specific fluid. Want to try a different one? You had to start from scratch. But with this chart, all you needed was a substance's critical point, just two little numbers, and you could get a darn good estimate of its behavior. It became an essential engineering cheat sheet, and honestly, it still is. But you know how it goes in science, right? This beautiful, simple model, well, it wasn't perfect. Reality, as it turns out, is always a bit messier. The thing is, the two-parameter model worked unbelievably well for some gases. I mean, the predictions were dead on. But for other substances, the real-world data just didn't line up. The predictions were always off. Something was clearly missing from the picture. And here's where they figured out the problem. For simple, basically spherical molecules like argon, the model was fantastic. But when you looked at more complex, lumpy, or stringy molecules like hydrocarbons, that's where the errors crept in. It turned out the actual shape of the molecule really mattered. And this is our next hero. Kenneth Pitzer comes into the story. He came up with a really brilliant way to account for the shape of things. He introduced a third parameter, this little guy, the Greek letter omega. This is called the acentric factor, and its whole job, its only job, is to be a correction for how not spherical a molecule is. So a perfectly round molecule like argon, its acentric factor is 0. A long, weirdly shaped hydrocarbon, it gets a higher number.
It's a single value that neatly packages up the molecule's geometry.
So Pitzer upgraded the equation. The best way to think about it is a base value plus a custom tweak. Your final compressibility factor, Z, starts with the baseline value for a simple spherical fluid. That's Z0. Then you add an adjustment, and that adjustment is the molecule's own personal weirdness score, omega, times a standard correction term. It was such a smart way to keep the original, simple idea, but just add that extra layer of real-world accuracy. Okay, let's tie this all together. Why are we talking about this today? Well, because this whole story, from a simple model to a more complex, accurate one, is just a perfect snapshot of how science works. And the legacy of this principle is absolutely everywhere in modern engineering. It's the bedrock for the super complex computer simulations we use to design things like chemical plants. It's absolutely essential for figuring out how hydrocarbon mixtures are going to behave. And it's the theoretical foundation for the famous modern equations of state, things like Peng-Robinson and SRK, that are the absolute workhorses of the entire industry. So in the end, what started as this simple thought that maybe all gases play by the same rules if you just know how to look, was tested, it was pushed to its limits, and then it was refined to become even more powerful. It's a story about finding unity in a complex world and building better and better models to understand it. And really, isn't that what science is all about? Thanks for joining me.